All right, you guys. So we're going to just talk real quick about bonding and classification of matter so that we can talk about what happens when atoms stick together, and we will all mean the same thing when we use different words. So hopefully you've already done your classification of matter POGL. If not, pause this video and go do that POGL first. It'll kind of walk you through things and help you make some logical sense out of it. There is a key posted for that, so you can also take a peek and just make sure you're on the right track. There are 3 classifications of matter that we care about. And so basically 2 of those are elements. So you can have atoms of an element, or you can have molecules of an element. Some atoms, or some elements, I should say, prefer to be single atoms. An example of that is helium or neon. Other elements like to form molecules. So examples of that are hydrogen, nitrogen, oxygen, fluorine, chlorine. Those all like to be molecules of 2, so we call them diatomic. But they're still elements, even though there's 2 atoms of nitrogen or whatever stuck together. Compounds are substances made from 2 or more elements bonded together. So if you have a hydrogen and an oxygen, now you have a molecule of a compound instead of just a molecule of an element. Pure substances are pure substances are when all of the particles present are identical to each other. So you can have a pure element that is single atoms, you can have a pure substance that is molecules of an element, and you can have a pure substance that is molecules of a compound. They're still pure substances because everything in the substance is identical. Mixtures, on the other hand, occur when there's more than one type of substance. So there's more than one type of element or more than one type of compound present, and they're not bonded together. So they're not sharing electrons or trading electrons or anything like that. They're totally independent of each other, and they're just mixed together. So now that we have that language, I want you guys to stop and do the bonding POGL if you have not already done so. And we're going to get into the specifics of how do things stick together to form compounds, whether that is a compound of an element or a compound of a substance. The periodic table can be used to predict what kind of bond we're going to form. If you have 2 nonmetals, it makes a covalent bond. If you have 2 metals, it makes a metallic bond. And if you have one of each, one metal and one nonmetal, that makes something called an ionic bond. And as you saw in the POGL, different things happen to the electrons in each of those situations. An exception to this is hydrogen. Hydrogen is on the left-hand side of the periodic table like it's a metal, but it's really a non-metal, and it kind of just does whatever it wants. So even though it's on the metal side, it usually acts like a non-metal and it bonds like a non-metal. So water is a great example of that. It's a polar covalent bond, so it's covalently bonded, sharing electrons. It's not sharing them evenly. And the oxygen and hydrogens are the ones that are sharing. And the oxygen holds on to the electrons a little bit tighter than the hydrogen can. And so that's just an example of how hydrogen bonds covalently and not ionically. Anyway, 3 types of bonds in a little more detail. Metallic bond is a fluid matrix of electrons holding together the metal atoms. And so in the image you can see it says a swarm of delocalized electrons, and it's all smeary. But basically all the valence electrons of the metal just kind of wander around and visit all the other atoms. And that's why metals conduct electricity. Electricity is just electrons, and they can just all wander around from atom to atom, and they're not specifically associated with any one atom. And sometimes this also gets called a sea of electrons. So your atoms are kind of suspended in this sea of electrons, and that's what holds them together. Next type of bond is the ionic bond, and it's a bond that occurs between two oppositely charged ions. Sodium has 1 lonely valence electron, and chlorine has 7 valence electrons. And gosh, chlorine would love to have 8 valence electrons. So it just casually snatches up sodium's electron. And then sodium's like, all right, this isn't the worst, because now it has kind of a full energy level, full octet. And chlorine's happy, it has a full energy level or a full octet. And so then everybody wins. And when that happens, sodium gets a 1+ charge because it lost a negative thing. Chlorine gets a -1 charge because it gained a negative thing. And then they can act like little baby magnets because we have a +1 and a -1. And that's what holds sodium and chloride together in salt crystals. The really important thing in ionic bonding is that the electrons get totally transferred to one of the atoms. And of course, we're talking about valence electrons. It doesn't transfer all of its electrons, right? It keeps its inside electrons, but any that are out in the outermost energy level could get transferred. Last type of bond we care about is a covalent bond. And this is when 2 or more atoms share valence electrons. Co means sharing, and then valent is referring to the valence electrons. That's where we get covalent from. So if you look at these 2 fluorines, they each have 7 valence electrons, and they really want to have 8. And so if they just get real close together, they can share these 2 electrons. So if you look at just the fluorine on the left, it thinks it has 8 electrons. And if you look at just the fluorine on the right, it thinks it has 8 electrons too. And everybody's happy. Another example of this is oxygen only has 6 valence electrons and it wants 8. And then hydrogen has 1 valence electron and it wants 2. So it gets right up close to the oxygen, and then each hydrogen shares its electron with the oxygen. And the oxygen shares 1 electron with each of the hydrogens. And suddenly everybody is energetically stable and happy because they think they have a full octet. And this is what allows covalent bonding to occur. So the electron clouds in this case are shared. Covalent polarity is something that's kind of in the middle between a non-polar covalent bond and an ionic bond. So in a perfect covalent bond, the electrons are perfectly shared. In an ionic bond, the electron, or electrons plural, are taken. So they're taken all the way away. And one of them gets a positive charge and one gets a negative charge. But in a polar covalent bond, they're sharing the electrons between them, but one of them is getting a little bit more time with the electrons than the other one. It's like when you share a piece of cake with your sibling, but you don't give them as big of a piece. So polarity ends up being the separation of charges due to the unequal sharing of electrons. So this guy over here, A, isn't as good at attracting electrons as B. And because of that, B is going to be a little bit negative and A is going to be a little bit positive. So that's where the poles come from, the opposite charges. Polarity is caused by differences in electronegativity between the elements. So we know that there can be some really large differences in electronegativity. If one thing is much more electronegative, it's going to try to pull all the electrons to itself. Now, if the other element is really, really weak, it's just going to take the electrons all the way away and make an ionic bond. But if the other element is kind of strong, it'll keep trying to hold on to its electrons as much as it can. And that's when we get this polarity happening. When molecules are polar, they have what we call a dipole, di meaning two, and poles meaning pole, like polar, like positive and negative. Oops, that was the wrong direction. One side of the molecule is slightly positive and one side is partly negative. And that, my friends, is all she wrote. So, when I'm back from Kansas, we'll be talking about a little more detail of discussing different types of compounds and how they're held together and how we talk about them. Thanks for listening.